Hello and welcome everyone. We are Team Sherlock and we work with Tivo on scene detection in broadcast television. I'm Jack.
I'm Brittany.
I'm Kevin.
I'm Hamant.
And our sponsors were Mark and Matthew with Tivo. So to give a brief overview on what Tivo is all about, they are the pioneers in the DVR, or the digital video recorder, which allows you to record shows on a cable stream and watch them anytime you want. They also bring viewers an experience that integrates traditional TV, such as cable, with next-gen TV, which is like Hulu Plus, Netflix, Amazon Instant Watch. So we had two projects for Tivo. Our first one, the goal was to create useful automated implementation of scene structures on video frame sequences in TV show episodes. In our second project, we were given free reign on a feature for Tivo's mobile app, which we'll talk about that more at the end of the presentation. So to give a brief overview on how our scene detection algorithm works, it records timestamps correlating with detected scenes and does this in an automatic process, going from a video file to a timestamp list. We focus on advertising spots for our algorithm as scenes and use three significant aspects of TV recordings: closed captioning, video, and audio.
We began our research by watching a lot of television and observing patterns and scene changes while we did that. We decided to come up with one method for scene change detection of using each of the main elements of a TV broadcast. And to focus on advertisements, we observed that an advertisement block is like many short scenes, and we decided to group those all together into one scene and detect the advertisement block as a single scene. The first observation we made was that a black frame tended to appear between scenes. We imagined that this may be sort of like a palette cleanser, a visual palette cleanser for the viewer in refreshing them and getting them ready for the next visual experience. And so our hypothesis was that when a black frame appears, that would indicate a change of scene. To gear this toward detecting the advertisement blocks, we decided to detect dense clusters of these black frame occurrences, as an advertisement block is just many short scenes. The next observation we made was in the audio realm. Similar to the black frame occurrence is a lack of stimulus between scenes, but in this case it was silence. We noticed that during scenes, even in quiet moments of a scene, there's still some ambient noise. And so our hypothesis was that a moment of true silence would only occur between scenes, if it was going to occur at all. And again, we looked for clusters of these silences to detect the advertisement block. The third resource that we had was closed captioning. Our initial inspiration to approach this was to look for key phrases, such as, "And now a word from our sponsors," or "Welcome back." We decided that would be too narrow of a scope for the shows, because many shows on television don't have phrases like that, and looked for other features that we could work with. We noticed that closed captioning companies don't have a standard for the formatting they use, and the formatting will vary between which company has done the authorship of the closed captions. Our hypothesis was that these companies wouldn't share the workload by splitting mid-scene, and so when formatting changes, that would indicate a change of scene. This turned out to be particularly useful in detecting these advertisement blocks, because each advertisement would come with its own closed captioning from a different company. Putting these ideas to work, we began with collecting data. To record shows, we selected a tool at HD Home Run Prime. It is open source. It has open source software that it comes with, and it also records in the MPEG transport stream format, which is a standard broadcast format for cable television. We initially wanted these features because we intended to manually extract the 3 elements from the broadcast recording. But we found that this would be quite laborious, and given our time constraint, we turned to third-party tools to help us do this. The first tool that we used was OpenCV. It's a library of visual analysis algorithms. OpenCV can't process the MPEG transport stream directly, so we needed a tool to convert the transport stream into a different format. FFmpeg is an assembly of multimedia tools, which we used to convert the transport stream into a QuickTime format, .mov, which could be processed with OpenCV. We also used FFmpeg to extract the raw audio track that could be processed for the audio algorithm. Finally, we used CC Extractor, which is it's a beta, it's still in beta, but it extracts closed captions from a variety of sources, including MPEG transport stream. We use that to get a text file that contained the closed captions along with their timestamps.
The design of our algorithms are based on hypotheses that we came up with early on, based on the patterns in video files for each data source. We had a set of hypotheses, we tested them, and some turned out to be true while others didn't. So we continued development on the hypotheses that turned out to be true. Each algorithm gave an output list of predicted locations of commercials inside of the given video file. The next step towards predicting commercial segments was the aggregation method. First, weights are determined for each algorithm based on their detection reliability using a training set. The gold standard is developed by hand for each video in the set and is compared to each algorithm's predictions of commercial locations. From this, we obtain an average reliability metric for each algorithm. This reliability metric is used as the weight. So by the end of determining the weights, each algorithm will have its own unique weight representing its reliability. The final predictions are computed by using an aggregate vote of weights for all time segments in the given video file. If the weighted positive vote is above a certain threshold, then that set time segment is adopted into the final list of predictions for that video file. Otherwise, if the weighted vote does not exceed the threshold or meet it, then it is rejected and it is not accepted into the final prediction. The scene detection algorithm applied to commercials was tested against a diverse data set. In our data set, there were many types of shows. The shows included both syndicated broadcasts and local broadcasts, and they reached out to a variety of different audiences. Because of this is a proof of concept that we have created a generalized scene detection algorithm. On average, 89% of our predictions were actual locations of commercials, and 78% of the commercial time in our data set of 20 videos was predicted by our algorithms. Some avenues for improvement may be to explore object detection, such as detecting when a logo shows up on the screen, or to detect drastic changes of color inside of the scenes to help us see where the commercials might be located.
So now I'll talk about the second project that was mentioned earlier, the app. So the idea is that a user of the app will be able to either like or dislike a certain TV show and give their evaluation on it. And the neat thing is that this will only show one show at a time, and a liked show will be stored for reference. And now it is possible to do channel surfing from anywhere, and this saves a lot of time and is more efficient rather than just like flipping through channels and wasting more time to see what show you want to watch. So this is the summary of our web app implementation from the point of view of both the server and the user. So the server will receive info and user info, show info and user info, and the database will have stored information about user-show relationships. The user will load the web page, and the server will display the show and user info, obviously. And by giving the evaluation, which will then be stored in the database, this will allow the user to get recommended shows, and this will allow the Tivo database to get feedback on the various shows. So what this means for Tivo is that Tivo will get more suggestions on recordings, and they will be able to identify correlations between many liked shows, and this also means for the user that they will be able to explore a lot of awesome features on this app, and they will be able to discover really awesome TV shows, and as mentioned earlier, they will not have to now surf through channels like flipping through them and wasting time. This means that they can get a show from anywhere, and this means also that there's an unrestricted pace for reviews. They can review anytime, any place. There isn't a minimum time commitment, and this is a very, very personal experience for the user. So, in summary, with this project, we were able to achieve the two objectives: a smooth process for creating scene change timestamps from a video file, and we were able to create an implementation of a web application. And this was something that we were given free rein with. Our sponsors told us that we could potentially try out exciting new ideas. So we really want to thank our sponsors, Matthew and Mark, for giving us the opportunity to work on this project. And we want to thank our professor, Richard Julig, and our TA, Grace Lynn, for really giving us the chance, as well as everyone else at UCSC who made it possible to do this project. Thank you.